Hello everyone. Yeah, as Mate introduced me, my name is Filip Morawski, and I came from Poland, where I work for Nicolaus Copernicus Astronomical Center. However, I'm also a member of a Virgo collaboration, where we study gravitational waves. And I generally am working in projects associated with the application of machine learning in our survey. And today, that's also something I would like to tell you about my research. But first, let's start from kind of tiny introduction into gravitational waves. So a little bit of astrophysics. I skipped all equations, so you will not get kind of confused with math. So gravitational waves, as in the kind of easiest description, are disturbances or ripples of space-time. Well, it might sound kind of confusing, but in general, it's pretty simple phenomenon. Because imagine, first of all, well, not imagine, but let's go back to the beginning of 20th century when Einstein derived his general theory of relativity. Because since that moment, we started to perceive gravity in a slightly different way. It wasn't force anymore in the same way as before. Rather, nowadays, we consider it as a kind of phenomenon resulting from the curvature of space-time. If this also sounds too complex, then let's just imagine space-time on a kind of flat plane, like, for example, this canvas. And when you put some mass, some kind of object onto such a canvas, what will happen is that it will appear kind of curvature around this object, like you can see here on that left picture. And of course, the bigger the object, the more massive it will be, the bigger curvature also will kind of occur. So the stronger the gravity, because simply the gravity is this kind of curvature that we are perceiving in this kind of material world in very simple terms. And according to general relativity, when such an object moves, also the curvature changes to kind of reflect the changes of the location of those objects with respect to the space-time. And what's more, when such an object is accelerating, it might produce, under certain conditions, gravitational waves. And those certain conditions are, for example, the following. Either you have two objects orbiting each other, like kind of two planets, two massive stars, or any kind of orbiting objects, or some asymmetrically spinning objects like neutron stars with some tiny asymmetries, like kind of tiny mountains on the surface. And in general, those gravitational waves are spreading across the universe with the highest possible speed, so the speed of the light, in a similar way that ripples in a pond on some kind of flat lake when you toss a stone into it. So generally, they contain a lot of information about those objects and the moment it was generated, and so on and so on. However, there is one particular feature pretty interesting when it comes to gravitational waves, that they stretch and squeeze everything on their path. In general, when it's a stretching is in parallel direction, squeezing will happen in perpendicular one. So unfortunately, I cannot show you this nice graphics that I found, because this is just PDF. But what I wanted to show here is that, well, one could say that we should see this phenomenon, because obviously considering the size of the universe, the possible number of kind of wave generators, everything should be squeezed and stretched. Yes, that would happen, of course, but at the same time, the amplitude of those waves, so those disturbances, are really, really, really tiny. So in general, the amplitude is dozens, some powers of magnitudes smaller than the size of the proton. So obviously, you need something more sophisticated to detect them. Fortunately, we are living in times that we have such a technology. Actually, it's not very new, because it's from 19th century. It's this, laser interferometry. Slightly more advanced than the one that Michelson and Morley created to study the light. But still, the kind of physical fundamentals are exactly the same. So, few words about this process. So, imagine that you have a laser shooting a beam into your device. Usually interferometers has this kind of L-like shape. And this kind of crossing point of the arms, you have a beam splitter, simply, as the name suggests, splitting beams in two. And each beam will kind of enter one of the arm through self-transparent mirror, like you can see here. So what's the whole reason for this, self-transparent mirrors? Because this additional part with respect to the basic interferometer. Because simply we would like to increase optical length of the light inside the arm. Because although our devices has 3-4 kilometers of length of those arms, but this is still not enough for the detection of gravitational waves. Actually, inside, this is called Fabry-Perot arm cavity, the light is being reflected hundreds of times. So actual optical length is bigger than 1,000 kilometers. So with such a distance, you might be able to detect even those tiny disturbances. Because when the light comes back to the beam splitter, in general, interferometry occurs. And as a result of interferometry, the light might be superimposed, but it might kind of, destroy itself as a kind of destructive interferometry. As a result of the destructive interferometry. And interferometers for gravitational waves are built in a way that if there was no gravitational wave passing through or any kind of thing that might influence the light, the path that light travels inside those arms, you will see nothing. So on photodetector, you will see no light at all. But if there was anything that influenced it, also kind of, sources, source noises, then you would see a tiny portion of that light. So what kind of signals you might see on that photodetector? So in general, there are two types of signal. Periodic one and, well, aperiodic. So aperiodic signals are originating from so-called mergers of some very large objects like some black holes or neutron stars or some mixed stars. And exactly that's something that we already detected a few times. However, what's more interesting for astrophysicists is our periodic phenomena. So kind of sources of periodic signals like rotating these non-axisymmetric neutron stars or wide binary systems, because we have much more sources like this in the universe. However, they are much more challenging to detect because obviously the amplitude of the signal is even smaller. Okay, so how such a signal might look like? Let's start from this kind of one-time cataclysmic one. So imagine that in some galaxy far away, a long time ago, there was some kind of binary system, a star that at some point the stars, those stellar objects started to be attracted toward the center of their motion. And in a moment, in such a moment, the kind of periodicity of the signal started to change, both with respect to the frequency and the amplitude. And that's exactly what you can see here. So the signal was kind of being stronger and stronger in time. And the moment when those objects merge, you obtain some kind of a peak, after which the signal vanished very fast. So yeah. Okay. So you will see so here you will see some results from the first detection of gravitational waves from LIGO in the United States, both interferometers. So in Hanford and Washington. Okay. So as you can see here exactly, they have the same shape as they have the same pattern as our models, because you can see here they slowly change in frequency and amplitude, and they reach this kind of peak when the objects merge, and after which the signal disappears. One thing also important to remember here are those spectrograms, because you can see here this chirp-like signal, which will be important slightly later when I will be describing some kind of artifacts in our data. But okay, what's the most challenging in the end, this kind of merging signals we are already able to detect. It's just a matter of sensitivity of our devices to be, even bigger and bigger, so you could just detect even weaker signals. But with periodic signals, it's not that easy, because they are about 3,000 times even weaker than those aperiodic ones. So as you might imagine, also everything hidden in the noise, which in itself might be non-Gaussian, so might have some kind of pattern. It's really challenging, and that's why machine learning might be pretty useful in this case. But before, let's speak a little bit about the methods of analysis that we have currently. So that method is called f-statistics, and it's based on Fourier transform. So this is kind of a simple graph describing the simulator of the signals that we are also developing. So in general, that's a kind of raw input time series data you have at the very beginning. Afterwards, you split such a data in some time windows chunks. For each of such a chunk, you calculate Fourier transform. In general, you have plenty of points on the sky around some point that you injected the signal. So you rather have some kind of a grid of points. And the next step you are doing, more or less, it's kind of comparing it with some models that we have, because in the end we know what kind of shape of the signal, what kind of pattern we are expecting. And if such a signal reaches some kind of threshold defined inside our method, we can consider it as a candidate for signal. It's not signal yet, because it might be some source, might be something that, some kind of artifact that only looks like gravitational wave. So further you have to also analyze it, either by analyzing coincidences of the signal in the following chunks of data, and see whether it, the frequency disappears at some points, maybe it changes over time, and so on and so on. And in general, that kind of underlying part in the middle is also a part that I used as an input data for first of my projects that I will cover in a moment. So just remember this step, that I have only candidates for signal. But okay, let's leave now astrophysics. And first of all, you might be curious why we decided to use machine learning. Well, there are plenty of reasons why you can do this. In the end, nowadays it's pretty popular as a method, or some kind of alternative method to do the same things that you usually do in some typical statistics or something like this. But actually there are some very good reasons for following this approach. Let's have a look on a few images or kind of curves, very well known in our collaboration. So first of all, sensitivity of our instrument. As you can see here, the sensitivity of our device changes pretty a lot over the range of frequency that we are analyzing. So obviously there are parts that we simply cannot use for detect signal, because the device is not sensitive enough. Another thing is that though interferometers are the most sensitive devices in the world, they detect literally everything, seismic noise, which is kind of large part of the noise in general, some planes, cars nearby, but even a bird's nest on one of the arm. Or something, once, the table in a control room was situated in a place that emitted some tiny vibrations that just, scientists show on the plot. So it's really everything. It can detect really everything. So besides you dive into analyzing the signal, you have to remove all this stuff. There's, some noises, some source of the noise are known, but most of it not yet. And that's why also this kind of unsupervised features of machine learning might be helpful in this case. For example, here you have one of the artifacts, so-called glitch, so transient noise event that might appear in your data. As you can see here, it looks similar to gravitational wave. And the shapes of those objects might be really very, very different. So you really always have to take in consideration that what you consider as a gravitational wave might not be in reality just kind of the signal that you are searching for. And in the end, we are searching for some patterns, complex patterns, hidden deeply in the noise. And well, it is known that machine learning in general is capable of at least solving part of those problems from which you know from other fields of science. So first of all, it is a promising tool in classification of complex patterns and weak signals. Maybe up to now no one used it for such a weak signal classification, but still, it's still worth to try and see what will happen. It might be essentially useful in the classification of periodic signals. Why? Well, as I mentioned before, we are using Fourier transform for analysis. So to search for periodic signals, actually the only thing you can use is the length of your data, because of course the longer you will have the signal and you will be searching for something that do not changes over time, you have a bigger chance of succeeding than analyzing a short signal. So and for such a long signals, Fourier transform might be pretty costly when it comes to computational power, especially that we would like to use it on some kind of online, so on the run when we are gathering the data. So it's always an alternative approach to current methods of analysis. So it's always good to have some tool with which we can compare our results. And as I mentioned before, it might be especially useful in case of noise characterization, which is pretty, hot topic now. But okay. Now I would like to describe you two projects that I started doing some time ago, that I'm still working on. So the general idea here was to focus on two aspects of signal that we are interested in. So first of all, we have pattern recognition of kind of distributions that we obtain. Another thing is time series analysis, because in the end we are searching for some periodicity in our data. And in that first project, I had kind of candidates for signal from F-statistics. So as you will see in a moment, those are just kind of 4 types of distribution as a kind of single instance of your data. So I generated those data for different signal-to-noise ratios as to see how our model will react toward those changes. However, bear in mind that we have our own definition of signal-to-noise ratio. So instead of just comparing the amplitudes, we are rather kind of integrating our whole signal, and there are 2 factors that are influencing the final value of SNR. So which is obviously the length of the signal, but also the amplitude of that signal. So in general, we consider SNR equal to 4 as a threshold, whether the signal might be considered as a candidate for just kind of some potential candidate for the signal. Okay, so now the plots. So we have 4 types of distributions: frequency, its derivative, and 2 coordinates, declination and right ascension. You might not know this system, but it's kind of commonly used in astronomy to describe points on the sky. So obviously you can see here that there are some patterns, some kind of shapes on each of those kind of distributions. And for signal, for the noise, and for stationary lines, so for some kind of artifact, let's say, those shapes might slightly be different. Especially for smaller signal-to-noise ratio, so closer to the threshold, we do not see those kind of differences. You might use these coincidences to compare, how it changes over time, but still, we are not focusing on this kind of aspect of our data. And that was whole idea here, to use convolutional neural networks to analyze it. But I wanted to use all of those data at once, so don't lose any kind of information that they might store. So instead of using one convolutional neural network, I decided to follow kind of it's a relatively new way of analyzing, processing your data, which is called multi-instance learning. So what's the difference with respect to this kind of typical neural, this kind of convolutional neural network, is that you have few, let's say, pipelines analyzing each pipeline, each convolutional network is analyzing different distribution, and at some point you combine those networks into one large network, and you process that's kind of combined information together further. So the results were kind of pretty promising because we were able to achieve about 95–96% of accuracy up to the threshold. Just really great, result. But what's even more interesting is that our model was able to correctly classify all the instances of the noise, which is really great because the only confusion that we had in this case was between the signal and the stationary line, so kind of glitch. However, things are not always as good as you would like to, because when we increase the frequency of sampling, so obviously we had much more points on our distributions. Well, the results were worse, and actually, I am still searching for the reason why it happened, because the only thing that changed was just the number of points on the image. Anyway, in the end, we are reducing the size of the image to save the memory, so it's always interpolated anyway. So the differences between them, if you would look on it, are not that big, but still, obviously the network has some problems, and either it's overtraining, and even if not, we obtain this kind of, about 10% or 20% worse results. So the next project was associated, as I mentioned before, with kind of, classification of periodicity. Here, since we're interested in kind of analysis of the evolution of the signal, we decided to use recurrent neural network, in particular, long short-term memory network that you already are familiar with. And what we wanted to focus here was different periodicity of our data. What does it mean? Because you might have just a periodic signal like a sinus, but you can have a modulation in amplitude, you can have a modulation in frequency, you can have other also types of modulation. And of course, each of those types of modulation might also differ regarding what kind of modulation and frequency, how this kind of how large is the amplitude modulating, and so on and so on. So we wanted to start from this kind of 4 classes, and of course taking into consideration the noise, and to see how well it will work. So those are the results. As you can see, it's nearly 100%, up to signal-to-noise ratio 1. So as long, and here the signal-to-noise ratio is this typical one, so we take into consideration here amplitude. So in this initial stage of that project, we just wanted to check whether LSTM will work better than convolutional neural network, because I also tried it before, one-dimensional CNN, and it turned out that with this kind of analysis, they're really terrible. They're really working well with aperiodic signals, but with periodicity hidden in the noise, even on the plots like here. So in the end, it's just a little bit noisy signal. It wasn't working too good. So that was great that it was able to in the end give you such a high accuracy. But at the same time, if you went deep down into the noise, so for example, that's the result for the classification based on SNR equal to 1% of the noise when it comes to amplitude. So something quite small, but still you can see something here. Of course, the total accuracy, well, it's not that good, but you can still see here that at least for this frequency modulation and this kind of just a sinus, the classification, it's quite good, because I'd say it's about 80%. For something, which in fact is just a noise with some kind of tiny disturbances inside, it can still see it. So that was also a pretty interesting result. That's something we would like to develop further, maybe making some deeper models. Well, anyway, what I wanted to do in those 2 projects, just to check whether we could use machine learning in our field, which is not kind of, this is not very common tool in astrophysics in general. It's actually nowadays it's becoming more and popular. But in the end, as for me, it looks like that, well, there are some problems, there are always some problems, but still, we had, well, at least I think that they proved that regarding pattern recognition, time series analysis, it works pretty well. And do we have some few minutes more? Or it's not 1, 2. Okay, because, well, since this is GPU Day conference, I wanted to tell you about some problems that we have using GPU. So, in particular, 2 problems that, well, it took some time to solve them. So the first time was the performance issue when I was using previous version of CUDA and TensorFlow. Because, well, I'm generally working on 2 types of graphic cards. One on my local computer, which is some GeForce Titan, something, relatively weak, and Tesla card on supercomputer. And after some time, I realized that actually my code during even debugging, so this kind of training, works faster than on supercomputer, on the Tesla cards. And really much faster, which is kind of, totally strange for me because, come on, it's impossible. In the end, it's one of the, that time, still it's one of the best cards on the market and it shouldn't happen. But, well, I was trying to search for it. Also some people were mentioning some issues regarding this TensorFlow, which is mostly problems with CUDA 7. I noticed, really person kind of experience in this field, so I had to struggle just and try to, kind of solution to it. But in the end, I didn't. But just an update to the newest version. So if you also have some issues regarding performance, I highly recommend moving onto CUDA 9.0 and TensorFlow 1.8 because it really works 3-4 times better. So another thing is parallel GPU. So during one of our tests, when we were using Horovod, which is kind of a framework developed by Uber for distributed TensorFlow computations, well, in the end, we just wanted to speed up our computations, but it turned out that when you are using kind of this computation or parallel GPU, we always got worse results than by using single GPU or this kind of mixed computing. So we started on single one and we trained our model on multi-GPU, or we did opposite. But as you can see here, the results were always good. So here on this kind of mixed or single approach, we always had better results regarding loss function. So well, I assume that it's somehow associated with averaging of the values after each step of the training, but still, I would say, well, I didn't expect that, this will be a source of, in the end, quite large difference, because, the 10% in difference regarding this particular loss function was quite a lot. So just to sum up, at the end, what are the plans for the future? Of course, solved the problems that we had. So regarding this overtraining for higher frequencies for F-statistics data, test our model on multiple GPU. Maybe in the future it will be easier to do this without this kind of loss of, let's say, accuracy at the end. Merge both LSTM and CNN into one large multi-instance learning, because in the end our approach was to create a large model that would be able to process different kinds of data but produce you just one single label. That's, let's say, this is signal, this is particular types of a noise, or this is just a noise, something like this. And the last thing, which we are interested into, is so-called child algorithm. So this kind of approach to learning based on similar way that humans are learning, because when you have a child, it usually starts learning from very simple examples of data, let's say, and slightly at some point it goes into more complex one. And well, after some tests of this approach, well, the results were kind of promising, because we were kind of using it for retraining over smaller and smaller SNR. And turned out, but for the smaller SNRs, it works perfectly fine. But at some point, it forgets to correctly classify the most obvious results. It's kind of also something I didn't expect. So just once more, this kind of take-home message. And thank you very much. If you have any questions, I'm more than happy to answer for them if there is some time, of course.
Yes, so let's thank the speaker. Very interesting with the machine learning applied to gravitational waves.
Regarding this is like since I worked for NVIDIA before, so regarding the choice of GPUs, I think having a Tesla and a Titan that doesn't say much. You need to also be sure about the chipset that you're using. That's for the first. And regarding multiple GPUs, I could only imagine. I mean, usually it should not make any difference in the algorithm. I don't know the exact algorithms that are being used in machine learning nowadays, but I can imagine that the newer GPUs...
Well, actually, the problem here in this case of this performance issue was that it was happening only sometimes.
A performance issue?
Yes.
Oh, not an accuracy issue.
Yeah. So
okay, performance issue could easily be about communication
yeah.
across the PCI bus. That's no doubt, yes. Otherwise, I just thought that maybe the newest features of the Volta GPUs, these neural network accelerators that they have inside of there, might have a different accuracy, for example. That might also make a difference in the accuracy of your models.
Yeah.
Okay, that's just what I wanted to mention.
Yeah,
Thank you.
Thanks.
Okay, so let's thank the speaker again.